All right, good morning, everybody. It's Mr. Willis again. I am going to, this first video is going to be about the constructive response questions I asked you guys to complete on Friday, May 1st. So you can see down at the bottom, I'm doing this as well, like I told you guys I would. So what I'm going to do is I'm just going to go through this list and I'm kind of going to talk. I'm going to give you a couple of pieces of evidence to answer these particular questions so you can go back and verify on your own whether or not your answers are good. I'm going to certainly take a look at the answers you guys submit to me, but I want you guys to be able to hear, me going over this material so you'll have something to reference as we move forward. All right, so we're going to kind of hit the ground running here because I know long videos don't work too well with you guys. So we'll kind of go from that. All right, so again, what we're doing is I gave you guys 6 constructive response questions. I have them up on the screen right here that I went over yesterday. I'm going to kind of talk about these as we move through the material here. Hopefully I can get this to work here. So we'll start with the first question here. Describe the plate motions along the Himalayan Mountains. Do you think these mountains are getting larger, smaller, or staying the same? Explain your answer. All right, so what we're going to do here is we're going to zip over to Google Earth real quick, and I'm going to talk about this. The Himalayan Mountains, for those of you who are not aware, are this mountain range right along here. I think it's something like 18 of the 20 tallest mountains in the world are located along this range. And what we have in this location is movement of the Indian subcontinent, the Indian subcontinent, and it is moving towards the Eurasian plate that we have up here. So we're getting what we consider here a converging boundary, right? So we've got this plate that's smashing into this plate here, and we're getting a huge amount of uplift along this range right here. So, and this movement is still continuing to the day. This is one of the most geologically active areas on the planet. So that is certainly evidence that these things are taking place. So to answer the question that I have on the sheet here, let me see if I can find it again. Whoop, that's for later. Do we think these mountains are getting smaller, larger, staying the same? The answer is larger. There is still uplift going on in those locations. Now, there's still destructive properties that are going along there as well, and that's going to be things like erosion, glacial erosion on the top of those peaks. So it's going to be a give and a take. There's some constructive and destructive things going on there, but overall, the Himalayan mountains are still getting taller, but that is being mitigated by the downward movement of the material along the mountain range itself, namely snow and glacial ice. Okay, so that's going to be our answer to number 1. So the answer to that particular one there is going to be it's getting larger. All right, so there's going to be an overall growth in those particular mountains. Okay, number 2, give Earth's history. Do you think there will be another supercontinent like Pangea? Explain your answer. Most scientists would agree that evidence suggests that we are going to see the continents move back together at some form much further into the future. Remember, when we talked about Pangea earlier in the year, we're talking about hundreds of millions of years ago for this big supercontinent to be in one particular location. If we go back and take a quick look at Google Earth again, we can see the overall movement of these plates. That's a little too far out, but we can see that parts of the plates, the Juan de Fuca plate here, are colliding with this. North America is moving towards the northwest. We've got movement here. We've got Australia and Micronesia, Indonesia are all moving towards the Asian plate. So yeah, there is certainly some evidence to suggest that these plates are going to come back together and form a new supercontinent. We're looking at that hundreds of millions of years in the future, though. So that's not going to be something that we have to worry about at any time soon. But this is also the underlying cause for all the volcanic activity that we see along the Ring of Fire, right? So the Pacific plate, the North American plate, the South American plate, the Oceanic plate down here. So the movement and the collapsing of the Pacific plate as these plates get pushed towards each other is going to be a large catalyst for those types of events. All right, so whoops, still back to that. All right, I got to make sure I go back to this one here. All right, let me clear the screen here. Provide 2 types of evidence that supports the theory of plate tectonics. I'm going to give you guys this link here. This is one that I thought was extremely well done. It talks about Alfred Wegener and his evidence that he used to support continental drift, and that evidence has been kind of assumed and utilized in this overarching concept of plate tectonics. So the big piece of evidence here is Gondwanaland down at the bottom, the supercontinent. Whenever Pangea broke up into Laurasia and Gondwanaland, there were 2 really big continents. One of them in the southern hemisphere is going to be Gondwanaland down here, and you can see the areas where all of these organisms have overlapping fossil evidence, right? So you have this fossil evidence of this frog rhino looking guy, Listerosaurus, in India, Antarctica, and Africa. And those three places are not very close together today. And this animal would by no means, as a land reptile, be able to swim across those oceans. So fossil evidence is going to be a huge factor in the support of that. The geologic fit of those particular plates, we can look at the rock layers that line up on South America and Africa. That's going to be one. Obviously the jigsaw puzzle look that we see here, where North America, the Saharan northwestern portion of Africa, where Greenland broke away from the European plate and the North American plate here. And then we can see the area that would have become the Caribbean Sea here as South America rotated away from Africa. So we can see where these particular things broke apart. There's glacial deposits. And when we look at the actual tectonic plates, we can see that, again, the same type of areas are going to have similar geologic deposits, which are going to be a piece of evidence that we can utilize for those things here. So that is a bunch of different types of evidence that you guys could use to support plate tectonics there. All right. The layers of the Earth stuff here. So let's zip through this pretty quick. Identify each of the three layers, X, Y, Z, labeled in the diagram. So X is the core, Y is the mantle, Z is the crust. Okay, describe one characteristic of a layer labeled X. All right, so when we're looking at the core, this is where a large portion of the Earth's mass is going to be located. It's primarily iron and nickel, and it is the hottest layer of the planet. We think it's primarily metal. So those are a number of characteristics. I gave you guys in the notes the specifics on how many kilometers thick we believe it is and things like that. You could certainly use those as pieces of evidence for that. Y, the mantle, right? So again, if you're kind of visualizing this as like a plum, the meaty part of the plum here, that would be the mantle. The pit would be the core. It is rock that is unusual in that it's fluid in nature. And by fluid, I mean it can move very, very slowly over time, and heat is going to be the major catalyst. So lots of iron, lots of magnesium, somewhere over the neighborhood of 3,000 kilometers thick. It is welded to the crust at the top, and then down at the bottom of the mesosphere, which is the bottom layer of the mantle here, we're going to see a lot of weird transitions between the outer core and this, where it's going to go to that liquid metal outer core to that very weird, rocky, liquidy kind of bottom layer in the mesosphere there. So that's what we're going to be looking at there. And then Z, the continental plates, or the crust, right, are going to be broken up into two types of crust. So continental and oceanic. Continental is made primarily of granite. Oceanic crust is going to be primarily basalt. Both of those have huge amounts of silicon and oxygen. Those are going to probably be the two primary materials that we find in the Earth's crust here. Remember, silicon is going to be found in silicates, which is sand, which we obviously have a huge amount of at the Earth's surface. And oxygen is going to get trapped in with all of these rocks. Think about the basalt chunks that I showed you guys in class and how it had that rusty kind of color to it. That's because the iron that was in that rock had bonded with that oxygen to create iron oxide, right? That was located in that particular one there. So those are a number of those. Again, you guys can go take a look at the notes that I provided to you guys last week for that if you need that. Question 5. During Earth's geologic history, the nature of geologic processes affecting the Earth has changed significantly. Volcanoes are an example of a system that has been very active over the history of our planet. Use your knowledge of Earth history and volcanism to answer these prompts. Explain how changes in the natures of volcanoes since the formation of the Earth. How have they and how do they change over time? Okay, so volcanoes can be active. They can be dormant. They can go extinct, right? So depending on if they're an outlet, right? So I've used this cake analogy a bunch here, but whenever heat wants to escape, it's going to create cracks. And think about a cake whenever you're cooking it. If you leave it in the oven too long, you get that crack that forms at the surface that allows the material to come out to heat to escape. Under the Earth, you not only have heat, but you've got a lot of pressure. So if you've got a tear in something with a lot of pressure, material is going to get squeezed out. So that's what we see here. So the changes in the natures of volcanoes just depend on their location. If we're looking at the Hawaiian Islands in particular, in the Pacific Ocean here, you can see that all of these are Hawaiian Islands, right? So these are the big islands down at the bottom, but Midway Island, which played a crucial role in World War II, is located up here. These are an area where the hot spot was located. So as the Pacific Plate moves to the northwest, these spots get burned through in these locations. So the nature of the volcano is, one, it's going to create a new island. So that's constructive. But the heat is the primary driver here. So once the volcano moves far enough from its heat source, it cools off and it kind of goes to sleep or gets dormant. And then over a long enough period of time, that can go extinct. So we've talked about that here. We've talked about it in the Grand Canyon area. Yellowstone is a very unique caldera that we talk about in these locations. Obviously, the huge mountain volcanic island arc that we have in the Aleutian Islands are all going to be examples of this. So volcanoes can create new land and they can destroy land. Obviously, that's going to be the constructive and destructive portions that we see in that. So which kind of ties into the second question here. Describe how volcanism is both destructive and constructive. One, obviously it's a process where things blow up, right? So there's going to be damage that can be taking place. Houses destroyed, biospheres affected, all of those are going to be destructive things. But on the plus side, they're constructive in that they create new land. Hawaii, rather, is a great example of this. The Hawaiian Islands would not exist without the lava that had flowed out of those shield volcanoes located on that hot spot in the Pacific Ocean. So if you go to Hawaii, there's all these beautiful beaches, there's these mountainy ranges that you see, and there's also layers of sediment and soil which have occurred because of the rock cycle over time in these areas. So volcanism builds up and tears down things, right? So, and then remember, at the mid-ocean ridge where the plates are cracked, they're going to be the force as that new material upwells through those crusts, through those portions there. It's going to be the thing that's pushing the earth around. So volcanoes play a very, very integral role in the Earth's geologic history and the way that things work. And obviously for humans, they play a pivotal role in our society. There have been huge eruptions in Earth's history that have caused some lingering changes to those particular areas and huge climactic shifts, right? So we talked about the year without a summer back in the 1800s when Krakatoa erupted. So those are all examples of those particular things. All right, so number 6 and the last question here, what have humans done to mitigate the dangers of geologic events like earthquakes, volcanoes, and tsunamis? Explain how we're better prepared to face these events now and hypothesize ways that can make us even more safe in the future. So places like California and Japan are great to talk about this. There's lots of earthquakes and seismic activity in those areas, so they make engineering building codes where buildings have to be built to code in those areas to be able to withstand earthquakes and tsunami-like forces. And that allows the people to escape from those buildings to do that. One of the ways is the way they design rebar inside of concrete. They'll put springs inside the concrete instead of just straight rebar to give the buildings an ability to flex and move a little bit to allow people to escape those buildings in the events of earthquakes and tsunamis. Volcanoes, this is the one that, again, we talked about the Mount St. Helens eruption, and volcanoes, we know when they're going to erupt generally, but we can't be as accurate as we are with hurricanes. So the only thing that we can do is warn people when these eruptions are going to take place and give them the information that we have on that so that they can make the best decision about their livelihoods that they can. And again, there are areas around the world that use volcanism to their advantage. Iceland has a huge amount of geothermal electricity that they generate from the heat underneath their island, which is volcanic in nature. So they boil water there. They use that to turn huge turbines to create electricity in those areas. So humans, for the most part, try to mitigate these things by building better, engineering better, trying to avoid areas where those things can cause some big problems and things like that. So certainly, I got a chance to read a couple of your answers, and you guys were pretty right on as far as that's concerned. As you guys finish this, and I know some of you didn't get through all the work this week, go ahead and get that taken care of and turned in to me. So hopefully this was useful to you guys. I wanted to make sure I went over this because this is kind of the core concepts of this particular unit. The next video you guys are going to get from me is going to be about the rock cycle, where we're going to kind of go over that. We're going to talk about those specific things. And again, we're going to try to bring all this material that we've talked about with Earth plate movement as a catalyst for change on the Earth's surface. So thanks again for listening. Hope you guys are doing okay. Send me a message through the Google Classroom if you have some questions. And if you're watching the video, let me know if you guys are interested in doing a little Google Meet where we can kind of sit and talk about some of this material. I'll look into setting one of those up if there's some interest. So on that note, you guys have a great day. It was good talking to you. See you later. Bye-bye.